Welcome to today's problem walkthrough. In this session, we'll explore problem number 1621, titled Number of Sets of K Non-Overlapping Line Segments. We'll dive into the key concepts, approaches, and techniques needed to solve this problem. Get ready to enhance your problem-solving skills as we break it down step by step. In this problem, we are tasked with determining the number of ways to form exactly K non-overlapping line segments on a straight line. The line is represented by endpoints, numbered consecutively from 0 to n1. A line segment is defined by two endpoints, I and j, where I is less than j. The key condition is that the K line segments must be non-overlapping. This means that for any two segments, they must not overlap in their ranges. However, they are allowed to share endpoints. For example, the segments 1, 3, and 3, 5 are valid because they only share the endpoint 3. The solution must return the total number of ways to form these K segments, modulo 10 to the power of 9 plus 7, as the result could be extremely large. The output of the problem is a single integer, which represents the number of valid ways to form K non-overlapping line segments, modulo 10 to the power of 9 plus 7. To understand this better, let's look at some examples. In the first example, we are given n equals 4 and k equals 2. This means we have 4 points on the line and need to form exactly two non-overlapping segments. The output is 5 because there are 5 valid combinations of line segments. For instance, one valid setup is to have the segments 0, 1, and 1, 2, where the two segments meet at point 1, but do not overlap. Another example is having the segments 0, 1, and 1, 3, where the second segment starts right after the first one ends. Continuing with the first example, some additional valid combinations include the segments 0, 2, and 2, 3, where the two segments are entirely separated by a gap. Another option is to use the segments 0, 1, and 2, 3, which are also completely disjoint. Finally, you can have 0, 2, and 1, 3, where the two segments overlap at a single endpoint. These 5 setups account for all possible configurations for n equals 4 and k equals 2. Now, in the second example, where n equals 3 and k equals 1, we only need to form one segment. The valid options are straightforward. You can pick 0, 1, 0, 2, or 1, 2. This gives us 3 ways to form the single segment, and the output is 3. In the third example, we scale up to a larger input with n equals 30 and k equals 7. Here, we need to calculate the number of ways to form exactly 7 non-overlapping segments on 30 points. The output for this case is a large number, 796297179, which is already modulo 10 to the power of 9 plus 7. This highlights the computational challenge of the problem, as the number of combinations grows significantly with larger values of n and k. The constraints ensure that the algorithm must be efficient, as n can go up to 100 and k can approach n1. This requires a well-optimized solution that avoids brute forcing through all potential combinations. Finally, let's address some important edge cases. For the minimum values, when n equals 2 and k equals 1, there is only one valid line segment, 0, 1. For maximum values, such as n equals 100 and k equals 99, the output will be extremely large, but it must still be computed efficiently under modulo 10 to the power of 9 plus 7. Another interesting scenario is when n is small but k is large, such as n equals 5 and k equals 4. In this case, the algorithm must carefully account for the limited number of points available. Additionally, shared endpoints must be handled correctly. For example, segments like I, j, and j, k are valid as long as they only share the endpoint j. The solution must ensure that all these edge cases are addressed while maintaining efficiency. To solve the problem of finding the number of sets of K non-overlapping line segments, the most intuitive approach is the brute force method. Here, we attempt to generate all possible subsets of K line segments using the given endpoints. For each subset, we check if the segments are valid, meaning they do not overlap, and then count the number of valid subsets. This can be implemented by using nested loops to create all possible line segments and testing every combination for the non-overlapping condition. However, the computational cost of this approach is very high. Generating combinations of points has a complexity of n squared, and checking all subsets of segments introduces a combinatorial blow-up. For large values of n, such as 10,000, this approach becomes infeasible due to its exponential time complexity. Instead, we can look to dynamic programming for a more efficient solution. By leveraging key observations about the structure of the problem, we can significantly reduce the computational overhead. In the dynamic programming approach, the solution revolves around an efficient state representation and recurrence relation. We define dp(i)j as the number of ways to form j non-overlapping line segments using the first I points. The transitions depend on whether we form a new segment ending at the current point or not. Specifically, the recurrence relation is dp(i)j equals dp(i1j) plus some dp(k)j1 for k less than I. The first term accounts for not using the current point to form a new segment, while the second term considers forming a new segment ending at point I, with k representing the starting point of this segment. To optimize the summation term, which would otherwise require O(n)² computations, we use prefix sums. This allows us to compute the sum in constant time, bringing the overall time complexity to O(n)*k). Additionally, the space complexity is also O(n)*k, making this approach practical for the problem constraints. For even greater efficiency, we can explore a mathematics-based optimization that uses combinatorics to calculate the number of ways to divide endpoints into k segments. By pre-computing factorials and modular inverses, we can reduce the problem to modular arithmetic. However, this approach introduces additional complexity and requires specialized knowledge of combinatorics. After evaluating the different approaches, we opted for the dynamic programming method as our strategy. This approach strikes the right balance between clarity, efficiency, and scalability. The brute force method, while straightforward, becomes computationally prohibitive for large inputs due to its exponential complexity. On the other hand, the mathematics-based optimization, though highly efficient, relies on advanced combinatorics and modular arithmetic, which can be less intuitive for many developers to implement. The optimized dynamic programming solution offers a clear and systematic way to tackle the problem. It efficiently handles the constraints of the problem while remaining accessible to a wider audience. By combining algorithmic insights, such as state representation and prefix sum optimizations, the DP approach emerges as the most practical and elegant solution. This makes it the best fit for solving the problem at scale, without sacrificing clarity or performance. In this problem, we are tasked with counting the total number of ways to form k non-overlapping line segments from a set of endpoints. The points are sorted in increasing order, which simplifies the process of defining line segments. A line segment is valid if it connects two points without overlapping any other segment. The goal is to determine how many such subsets of k segments can be created. To achieve this, we'll break the solution into clear steps, starting with understanding the input and output. The input consists of endpoints and the integer k, which specifies how many segments we need to form. The output is the total count of valid subsets of these k segments. By following a structured approach, we can tackle this problem efficiently step by step. The first step is to generate all possible line segments from the given points. A line segment is defined by two endpoints, and since the points are sorted, we can ensure that every segment is represented in the form p_i, p_j, where I is less than j. This process involves iterating over all pairs of points, resulting in a time complexity of O(n)², as there are a total of n. Choose two possible pairs. Once all segments are generated, we store them in a list called segments for further processing. Next, we need to ensure that the segments do not overlap. To do this, we define a helper function called is_non_overlapping. This function checks whether two segments are non-overlapping by verifying that one segment ends before the other begins. Specifically, for segments A, B, and C, D, they are non-overlapping if B is less than or equal to C, or D is less than or equal to A. Since this check is straightforward, it runs in O(1) time. After that, we focus on generating all possible subsets of k segments using the itertools.combinations function in Python, which efficiently produces combinations of a given size. This step has a time complexity of O(n)² k, where C represents combinations, and it lays the groundwork for filtering subsets in the next step. Now, we focus on filtering the subsets to ensure that only valid ones are counted. For each subset of k segments generated in the previous step, we use the is_non_overlapping function to verify that no two segments in the subset overlap. This involves comparing all pairs of segments within the subset, which takes O, k squared, time per subset. If a subset passes this validation, it is added to the count of valid subsets. To track this count, we maintain a simple counter variable. Once all subsets have been processed and validated, the counter will represent the total number of valid subsets of k non-overlapping segments. This step is critical because it ensures that our result adheres to the problem's constraints. Along the way, we leverage efficient data structures like lists for storing segments and combinations generators to minimize overhead. With the subsets filtered, the final step is simply returning the count of valid subsets as the result. This problem highlights several key insights. The most important aspect is efficiently checking for overlaps between segments. By presorting the points, we simplify the process of defining and comparing segments, making the overlap check both consistent and efficient. Additionally, while the brute force approach generates all subsets and then filters them, we can optimize this process. For instance, we could prune invalid subsets early during generation, skipping further checks if adding a new segment causes overlap. However, even with optimizations, the brute force approach can become computationally expensive for large values of n and k due to the combinatorial explosion. Advanced techniques like dynamic programming or segment trees can help scale the solution for larger inputs. When analyzing complexity, the time cost is dominated by the subset generation and filtering steps, leading to an overall complexity of O n squared, k/k. Asterisk k squared. The space complexity is also significant due to the storage of combinations. Finally, we must account for edge cases. For example, if k is greater than n, forming k segments is impossible, so we return 0. Similarly, if k is 0, the empty subset is valid, so we return 1. If n is less than 2, no segments can be formed, and again, we return 0. The problem does not require special handling for collinear points since segments depend only on their endpoints. With these insights and considerations, we have a comprehensive understanding of the problem and its solution. Here, we start by defining the function number of sets within the solution class. The parameter n represents the total number of points, and k is the number of non-overlapping line segments we want to form. We initialize a constant mod to handle large numbers since the result needs to be returned modulo 10 to the power of 9 plus 7. Next, we define a 2D list dp, where dp, I, j, will store the number of ways to form j segments using the first I plus 1 points. Similarly, we create another 2D list prefix to optimize our calculations by maintaining prefix sums, which will help in quickly summing up relevant subproblems. To handle the base case, we set dp, I, 0, equals 1 for all I, because there is exactly one way to form 0 segments, by taking no segments at all. We also initialize the prefix sums for j equals 0 with the same values, as the prefix array will store cumulative values of dp. After setting up the base case, we move on to filling the dp table for all possible numbers of line segments and points. For each segment count j from 1 to k, and for each point I from 1 to n1, we calculate dp, I, j, in two parts. The first part adds the number of ways to extend a segment ending at any index less than I, which is stored in prefix, I1, j1. The second part includes the ways to continue without forming a new segment, which is represented by dp, I1, j. Finally, we take the modulo of the sum to ensure the result stays within bounds. We then update the prefix array by adding the current dp, I, j, to the cumulative sum stored in prefix, I1, j, again taking modulo mod to prevent overflow. After completing the nested loops and filling the dp table, we return the value stored at dp, n1, k. This entry in the table represents the total number of ways to form exactly k non-overlapping line segments using all endpoints. By leveraging dynamic programming and prefix sums, we ensure that the solution is both efficient and optimized for larger inputs. This concludes the implementation of the function. Here, we start by defining the number of sets method, which takes two parameters, n, the number of points, and k, the number of non-overlapping line segments we need to form. We declare a constant mod to ensure our results fit within the constraints of large numbers, as the problem specifies modular arithmetic. Next, we initialize a 2D array dp, where dp, I, j, represents the number of ways to form j segments using points from index 0 to I. Additionally, we introduce a prefix array to store prefix sums, which will help optimize our calculations by avoiding redundant computation. The base case is simple. If we need to form 0 segments, there's exactly one way to do that, by not selecting any segments. So, we iterate through each point I and set dp I, 0, and prefix I, 0, to 1. With the base case set up, we move on to filling the dp table. For every segment count j from 1 to k, and for every point I starting from 1, we calculate dp I, j. First, we account for the number of ways to extend a segment ending at any index before I by using the prefix array. This value is stored in dp I, j. Then, we add the number of ways to continue without forming a new segment, which is simply dp I1, j, and ensure the result fits within the modulo constraint. To optimize further, we update the prefix array for each point I and segment count j. This is done by adding the current value of dp I, j to the prefix sum of the previous point for the same segment count, ensuring the result is taken modulo mod. The prefix array allows us to efficiently compute the sum of all values in dp4 indices less than I, which is critical for reducing the complexity of our solution. Once the dp table is fully populated, the result we need is stored in dp n1k, which represents the number of ways to form exactly k non-overlapping line segments using all endpoints. This value is returned as the final answer. By combining dynamic programming with prefix sums, we achieve a highly efficient solution to this problem, ensuring that all constraints are met even for large inputs. In this problem, our goal is to determine how many ways we can select exactly k non-overlapping line segments from endpoints arranged on a 1D line. Each line segment is defined by choosing 2 distinct points, and no 2 segments are allowed to share any points. Let's start with an example where n equals 4 and k equals 2. Here, we initialize the dynamic programming table dp and the prefix sum table prefix, both of which will help us compute the result efficiently. The table dp I, j represents the number of ways to select j segments from the first I points. We also set up modular arithmetic with mod equals 10⁻9 plus 7 to handle large numbers. For the base case, if no segments are to be formed, there's exactly one way to do so, which is to not select any points. This means dp I, 0, equals 1 for all I. The prefix table is initialized similarly, where prefix I, j stores cumulative sums of dp values up to I to optimize summation calculations later. After initialization, both tables are ready to be populated for higher values of j. Now, we populate the dp table for the case where j equals 1, meaning we are forming exactly one line segment. The idea is to extend a segment ending at each point I using points before it. For I equals 1, the only segment we can form is from point 0 to 1. Here, dp 1, 1 is updated using the prefix sum of dp 0, 0, and remains 1. Similarly, for I equals 2, we calculate dp 2, 1 by adding the prefix sum of dp 1, 0, and dp 1, 1, resulting in 2 ways to form one segment. For I equals 3, we extend segments ending at previous points and find that dp 3, 1 equals 3. At each step, we also update the prefix table to maintain cumulative sums, which will be helpful for further calculations. By the end of this step, the dp table reflects all possible ways to form one segment using up to 4 points. Next, we calculate for j equals 2, where we aim to form 2 non-overlapping segments. For I equals 2, we extend segments using the prefix sum of dp 1, 1, resulting in dp 2, 2 equals 1. At I equals 3, we use the prefix sum of dp 2, 1, and add any valid configurations from dp 2, 2. This gives dp 3, 2 equals 4, which represents the number of ways to form 2 segments using up to 3 points. The prefix table is updated accordingly to include these new values. Finally, we observe that dp 3, 2 gives us the result for this example. There are 4 ways to form 2 non-overlapping segments using 4 points. This demonstrates how the dynamic programming and prefix sum approach efficiently calculates these values. Let's now consider another example with n equals 5 and k equals 3. Here, we initialize the tables just as before, with the base case dp I, 0 equals 1. To fill the table, we calculate dp I, j for each combination of j segments and I points. For j equals 1, we compute the number of ways to form one segment using up to 4 points. Then for j equals 2, we calculate the configurations for 2 segments, and finally for j equals 3, we determine how to form 3 non-overlapping segments. The final result is stored in dp, 4, 3. A key insight from this solution is the use of the prefix table to optimize summation, reducing the complexity of calculating cumulative sums. Additionally, modular arithmetic ensures that our computations remain efficient and avoid overflow when dealing with large numbers. This approach effectively combines dynamic programming and cumulative sums to solve the problem in a structured and efficient manner. The time complexity of our solution is n*k. Let's break this down. First, during initialization, we set up 2 arrays, the dp array and the prefix array. These have dimensions of nx, k plus 1, meaning that initializing them takes n*k operations. However, since this is just a one-time setup, it doesn't impact the overall asymptotic complexity of the main computation. Next, in the dynamic programming step, we have 2 nested loops. The outer loop iterates k times, once for each segment we want to create, while the inner loop iterates n times, once for each point. Inside the inner loop, the operations, such as accessing values from the dp and prefix arrays, performing addition and modulo operations, and updating the prefix array, all take constant time, or O1. Therefore, the total complexity of the dynamic programming process is k*n*1, which simplifies to n*k. When we combine this with the initialization step, the overall time complexity remains n*k. Now let's discuss space complexity. The space complexity of this solution is also n*k. This comes mainly from the dp array, which stores the number of ways to form j segments using points 0, I. The dp array alone requires n*k space. Additionally, we use a prefix array to optimize our calculations by storing prefix sums, and this array also has the same size, n*k. Since both arrays are of equal size, the total space usage is n*k. Importantly, this space usage is consistent regardless of the input, as the dimensions of the arrays depend only on n and k. Finally, when considering the best, average, and worst cases, the time and space complexity remain the same. This is because the algorithm systematically computes results for all points and segments without any early exits or conditional optimizations. To put the efficiency of our solution into perspective, let's compare it to a naive approach. With a naive approach, we would recursively try all possible ways to form k non-overlapping line segments from n points. This would involve generating all possible subsets of points, checking each subset to see if it forms valid, non-overlapping segments, and then counting the subsets that form exactly k segments. The complexity of this naive method would be exponential, 2 to the power of n, because of the need to generate and validate all subsets. In contrast, our optimized dynamic programming solution reduces the complexity to n*k. This improvement is achieved by systematically computing the number of valid segment sets using dynamic programming and leveraging prefix sums to avoid redundant calculations, making the process much more efficient. Finally, let's solidify our understanding with a mathematical justification of the time complexity. The dp array has dimensions nx, k plus 1, meaning there are n*k plus 1 entries to compute. Each of these entries is calculated exactly once. The computation for each entry involves constant time operations, such as addition, modulo, and array lookups, which means the time taken per entry is 1. Multiplying the number of entries by the time per entry gives us a total of n*k operations. This confirms that the time complexity of the solution is indeed n*k. Similarly, the space complexity is n*k, because we store both the dp and prefix arrays, each of which has the same dimensions. This efficient use of time and space highlights the strength of the dynamic programming approach compared to more naive methods. When tackling this problem, there are a few common mistakes to watch out for. First, not accounting for edge cases involving overlapping segments can be a critical oversight. For example, if segments share points or overlap, this can lead to solutions that violate the non-overlapping constraint. Always verify the problem's requirements carefully to avoid such errors. Another pitfall is relying on inefficient brute force methods for large input sizes. Generating all possible subsets may work for smaller values of n, but as n grows, this approach quickly becomes computationally infeasible. To address this, consider pruning invalid subsets early or leveraging dynamic programming to reduce the overall state space. Additionally, be mindful of off-by-one errors when working with segment indices. Mismanaging inclusive and exclusive boundaries can lead to segments that either cross limits or omit valid solutions entirely. Lastly, don't overlook constraints on k, the number of segments. If k is too large or too small relative to n, you might end up generating invalid solutions, so always validate the feasibility of k before diving into computations. Overcomplicating your solution can also lead to unnecessary challenges. Using extra data structures or over-engineering the logic can increase both time and space complexity, so it's best to stick to the simplest approach that fulfills the problem's requirements. Now, if you're in an interview setting, there are a few key points to keep in mind. First, systematically breaking down the problem is crucial. Start with the brute force approach to demonstrate your understanding, then discuss how you could optimize it. Interviewers also value your ability to communicate trade-offs. For instance, explain the limitations of brute force and how techniques like dynamic programming or greedy methods address those inefficiencies. Testing edge cases is another vital step. Always consider scenarios such as the minimum and maximum input sizes, situations with no valid solutions, and cases involving overlapping segments. Finally, be clear about your thought process throughout. Even if your initial approach isn't optimal, showing how you refine and improve your solution demonstrates your problem-solving skills. This problem shares similarities with several related problems that can help deepen your understanding. For example, LeetCode 1027, longest arithmetic subsequence, and LeetCode 300, longest increasing subsequence, both involve optimizing sequences under specific constraints. LeetCode 354, Russian doll envelopes, and LeetCode 406, queue reconstruction by height, also require strategic thinking to manage relationships between elements. Exploring these problems can provide valuable insights and techniques that apply here. Additionally, alternative approaches can be helpful depending on the problem's constraints. A greedy approach focuses on choosing the smallest or largest possible segment at each step to minimize overlap. However, this method may fail in cases requiring global optimization. Dynamic programming is a more robust option, where you define a DP table to track solutions based on the first I points in J segments. While this guarantees correctness, it often comes with higher space complexity. Lastly, backtracking with pruning is another strategy. Here, you generate subsets recursively, but prune invalid solutions early to save time. This method is slower than dynamic programming but easier to implement for smaller input sizes. Great job making it to the end of the session. Today, we reviewed how to solve problem number 1621, discussed key algorithms, and highlighted optimization strategies. Remember, consistent practice and learning from problems like these can elevate your coding skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!